Assalamu alaikum everyone. Okay, now we will continue with chapter 4.4b, which is reactive process, where we're gonna solve it using atomic species balance. So we will see an example representing this method. Okay, let's recall back exercise 1. So let's read together. Here, in a Deacon process for the manufacture of chlorine, so chlorine is our product, hydrochloric acid and oxygen react to form chloride and also water. So we have here HCl plus oxygen to get Cl2 and H2O. Sufficient air, which represent by 21 mole percent of oxygen and 79 mole percent of nitrogen, is fed to provide 35% excess oxygen, and the fractional conversion of HCl is 85%. So we have two specifications here. Based on the HCl molar flow rate of 100 mole per minute, so we have one value of inlet here. Perform the degree of freedom analysis, and then calculate the mole fraction of the product stream components using the extent of reaction, molecular species balances, and atomic species balances. So for today, we're going to learn how to solve it using atomic species balances. So here we have this chemical equation. What we need to do is first we need to balance the equation. Here we have HCl plus oxygen to get chloride and also water. So when we balance it, we have here 2, here is 0.5, 0.5 here. Okay, and then Cl2 plus H2O. Okay, let's solve it using the atomic balance. Okay, first is the stoichiometric chemical reaction. Just now we already solved it. We have 2HCl, we react with 0.5 oxygen to get Cl2 plus H2O. Then we draw the flow chart based on the information. So here we have 100 mole per minute of HCl given by the question. And then we have another feed, which is air. So air is a mixture of oxygen and also nitrogen. So after the reaction, so we have a reaction here involving HCl and oxygen. We're gonna have product, which is Cl2 and H2O. But in the end, we're gonna have 5 components in total, which are Cl2 and H2O as the product, HCl and oxygen as the reactant, and also nitrogen. Why nitrogen is here? Because we have air here. So N2 exists as inert. It exists because our inlet is air, a mixture of 21% of oxygen and 79% of nitrogen. Then we have another specification. One is the air is given 35% excess of oxygen. And then we have another specification where the conversion of HCl is equals to 0.85. So here, the conversion is explaining about the conversion of HCl. That's why if you remember, the formula for conversion is how much mole of things reacted over how much fat. So here we know already 100 mole per minute is fat. So here we can write 100 mole per minute. And then how much reacted, that will be how much fat minus the output. So we have here 100 minus N3. So basically from here we can solve one lah. Okay, but let's not proceed. Now we detail out more. We have another more information, which is the 35% excess of oxygen. That is another specification. And then we have the composition here, 0.21 mole oxygen per mole and 0.9 mole nitrogen per mole. So for input, no problem. For the output, we can choose whether we want to represent it using molar flow rate of each component, or we can represent them using the fraction And also we have here the flow rate of the output. So if we choose the fraction, then y5 can actually just be represented with 1 minus y1 minus y2 minus y3 and minus y4. So become in total 1 plus 4 variable lah. So total 5. So or we can choose as 5 variable here. So you can choose either approach. Either you want to represent as the molar flow rate of each compound, or you can represent by the molar flow rate of the mixture and also the fraction of each compound. Let's say we focus on the first method, right? Now, how much is the basis? Remember back last time, how do we decide on the basis? Are we going to create a new value for the basis? What we have to do is first we have to solve the DOF, the degree of freedom. If DOF is equals to 0, we should not create any number. We should simply take from the chart. So here, I already give that the basis is 100 mole per minute HCl feed. So I've taken this value, the feed, as the feed of HCl as the basis. So is it true that the DOF is equals to 0? Now let's see. Okay, remember we are now solving the mass balance using atomic species balance, not extent of reaction, not molecular species balance. We are using atomic species balance. So the general balance for atomic species is input is equals to output. So that we have to solve using degree of freedom analysis. Okay, so how many unknown label variables we have? So remember back, we have the flow chart. So we have here HCl, which we know. HCl is 100 mole per minute here. Then we have the air. The air, we don't know how much is the value. We have N air. Then we have the output. Let's say we choose to represent it using the molar flow rate of each component. So we have here N1 of Cl2. We have N2 of water. Water here. We have N3. So this NN is representing the molar to represent amount of HCl. So N3 mole of HCl, N4 mole of oxygen. And don't forget, you have the excess, you have the inert, which is the nitrogen. So N5 for nitrogen. So how much number of unknown label variables? We have 6, and air, and also N1 up to N5. So 6 unknown label variables. How many independent atomic species balances? So remember back the equation, we have 2 HCl plus 0.5 oxygen to get Cl2 and water. So we are referring to atom. How many atom we have here? We have H, we have Cl, we have oxygen. So here we have a nitrogen, right? So here, number of independent atomic species balance is HCl and O lah, because nitrogen is inert. And then we have number of molecular species balances on independent non-reactive species. This is nitrogen. But if you get confused, you can simply choose both lah. So we have here hydrogen, we have Cl here, we have oxygen here, O lah. Then we have N from here. So in total, we have 4. So minus 4. And let's see, do we have any more specification? Yeah, we do have specification. We have 2 specification. One is the 35% of excess of oxygen, and then 0.85, 85% HCl conversion. So 6 minus 3 minus 1 minus 2, you got 0 degree of freedom. So the 0 degree of freedom, so the problem can be solved and you don't have to create a new value for the basis. You can simply choose the value in the flowchart. Okay, so now let's solve it using the atomic species balance. Let's start with how do we solve an air using the information of 35% excess of oxygen. Remember back the equation, we have here 2 HCl plus 0.5 oxygen to get Cl2 plus H2O. Okay, so an air, how much is air? So we know that the inlet for HCl is 100 mole HCl per minute. This is our limiting reactant because air is put in excess. And from the molecular equation here, we can see that for every 2 mole of HCl reacted, 0.5 mole of oxygen should be reacted. And then we know that we are supposed to give only 100% of oxygen or 1 mole oxygen, but we give excess 35%. So we put here 1.35 mole oxygen fat instead. Then we know that in the air, we have for every mole of air, 21% is oxygen. So 0.21 mole of oxygen is fat in the air. So solving this, we know that an air in the feed is equals to 160.7 mole air per minute. So we solve one variable. Next, what's we're going to solve? Let's use the second information, the second specification given by the question. So the specifications say that we have here 85% HCl conversion. That will be how much excess, how much unreacted. We have 15% remains unreacted. So we can solve for N3. So here N3 is representing the excess of HCl. So solving it, N3 is equals to the fat, which is 100 mole per minute HCl fat, times 0.15 here. 15% unreacted. So 0.15 mole unreacted for every fat. So we solve it, we got 15. If you got confused, you can remember back the equation for conversion. So remember, conversion is equals to F is equals to how much mole reacted over how much fat. So here how much reacted? We have here 85% reacted out of 100. So 85, 0.85 times 100, we got 85. How much is the fat? Fat is 100. So this is 0.85, right? Or if you want to relate with N3 lah, like just now I showed in the equation. Let me just clear up this thing. Okay, we can use the conversion equation. F is equals to how much reacted over how much fat. We know already how much fat is 100. How much reacted? That will be 100 fat minus unreacted material, which is N3, over 100, which is the fat, is equals to 0.85. This is in the previous slide that I showed, 0.85. Then you can solve for N3. You will still got N3 is equals to 15. So now you solve for NA and you solve for N3. Okay, let's solve the others. Okay, let's solve using N balance because we have several balance, right? We have 4 atom and Cl, O, and H. So first we start with N balance. Using N balance, we can solve N5. N5 represent how much nitrogen in the output. So for N balance, so I have written here actually reversely. Here we have the inlet or input. This is our output lah actually. So our output, for every 1 mole of nitrogen, Here we have nitrogen. For every 1 mole of nitrogen, there is 1 mole of N2. There must be 2 mole of N. There is 2 here. And then our output is N5. So that is output. How about input? Remember that for every 1 mole of air, we have 79% of nitrogen, N2. And for every 1 mole of N2, there is 2N here, so 2 mole of N. And we know that the input for air is 160.7 mole per minute air. That is an air that we solved just now. So we have only one variable here, which is N5. We can solve for N5. We get 127 mole nitrogen per minute. Okay, that's for nitrogen. Then we solve using chloride balance, Cl balance. So we also do for input is equals to output. So N1 is referring to how much Cl2 as the product. So we can solve for N1. So remember back the equation, we have here 2HCl plus 0.5 oxygen reacted to get Cl2 and water. So here we have the input, 100 mole of HCl. So we're going to choose all compound that have Cl in it. So the input, what compound does having Cl? Only HCl have Cl. Oxygen doesn't have Cl. So for every 100 mole of HCl, we have to times with 1 mole of HCl inside, we have 1 mole of chloride. This is the input. How about the output? So we have output chloride comes from Cl2. Here, it did not come from H2O, but remember that we also have excess HCl. So here we have 1, and then we're going to have Cl from HCl as well, because there are 15% excess. So if we go to the excess of HCl, we have 15 mole HCl per minute excess. And for every 1 mole of HCl, there will be 1 mole of Cl. So we add up with whatever in the Cl2. So for every 1 mole of Cl2, because there is 2 here, we have 2 mole of Cl. And how much is N1? N1 is the thing that we're going to solve. So solving this, we will get N1 is equals to 42.5. So we have here, we can solve this basically using how much as input will be equals to the output. Okay, similarly, we are going to do the same for the other atom. We're going to do the same for hydrogen and also oxygen. Okay, let's see for hydrogen, the input for feed. What is the compound that have hydrogen? We have only one, which is HCl. We have another compound, which is oxygen, but it doesn't have hydrogen. Nitrogen as the inlet also doesn't have, so we have only one. So we have 100 mole of HCl per minute as the feed, and for every 1 mole of HCl, there will be 1 mole of H. That is our input. Then let's see our output. Where do we have hydrogen? So we have hydrogen here in water. Another thing is we will have it in the excess of HCl, the one that's not reacted. So how much HCl not reacted? We have 15 mole HCl per minute not reacted. And for every 1 mole of HCl, there is 1 mole of H. Add up with the H from the water. We have output N2 mole H2O per minute as the output. And for every 1 mole of H2O, there is 2H here. So there is 2 mole of hydrogen. So here we have 100 is equals to 2N2 plus 15. Solving it, we get N2 is equals to 42.5. Finally, we can solve for oxygen. So here, oxygen, the inlet, where do we have oxygen? We will only have oxygen here. So let's see the input first, the inlet first. We know that for every 1 mole of air, there will be 21% of oxygen. So 0.21 mole oxygen. We know that air is present as 160.7 mole per minute of air. And then we know that for every 1 mole of O2, there will be 2 oxygen, 2 oxygen atom here. So that will represent the input. And how about the output? So we will have output from water here, and we will also get the output from oxygen. Why? Because the question already mentioned that oxygen was put in excess, 35% excess, if you remember. So let's see from the water, how much O is in the water. So how much water is there? We solved it previously already. Water is 42.5, the N2. So water times how much oxygen in water. For every 1 mole of water, there is one only oxygen. So 1 mole of oxygen that is in the water. Add up with the excess oxygen. So here, how much is the excess oxygen? That will be represented by N4 that we want to solve. So we have N4 mole oxygen per minute. And for every 1 mole of O2, we have 2 mole of oxygen atom. So solving this, here we have already 160.7 times 0.21 is equals to, or times 2 is equals to, here we have 2 and 4 plus 42.5. Solving it, we will get N4 is equals to 12.5 mole oxygen per minute. Now we have solved all of the variable. So knowing all of the variable, knowing N1 up until N5, we can actually calculate the flow rate of the mixture by simply adding up N1 up until N5 to get the mole fraction of the product. So we have add up N1 up until N5, we got N product is equals to 239.5 mole per minute. Then we can find the mole fraction of each product. So Y1 will represent the mole fraction for Cl2. So here we have YCl2 is equals to N1 over N product. So here N product we got from here, and N1 we solved it previously, then you got 0.177. We do the same for all, so we got the mole fraction of all product. Okay, so that's all for this lesson. We're going to continue for molecular species balance in the next lesson. All right. Thank you everyone for listening.